So I think we are on. Yes, cool. Okay, so today we're going to be doing a study club on the ZEXE, Z-E-X-E paper. This session will be led by Youssef, so thank you for doing that. And given the size of this paper and sort of the depth of it, we decided to break it up into 3 parts, which is hopefully the right amount. I know even the first part was still pretty dense. Like first half of the first part was easy, and then it got more intense. Yeah. But Youssef, do you wanna take it from here?
Yeah, sure. So just to present myself, because I think we haven't been introduced to each other, I met a few of you in Berlin in ZK summit. So I am a cryptographer and I work at EY, so mainly on privacy issues. So today we will talk about the ZEXE paper. So yeah, so we wanted to break this down to 3 parts. So this one will cover until page 21, I guess. So yeah, so the first part of this paper is somewhat an overview of all the papers. So we're going to go through all those contribution in this paper, but not maybe pretty much in details. So so I prepared some notes as I was going through the paper. So yes, so the main point of the paper was to perform offline computations and then upload a proof of correctness of the computation to the ledger. So the proof should be zero knowledge, constant size, and constant time verification. So as we love. So obviously we're talking about ZK snarks here. So how they want to do this is they introduced a new cryptographic primitive. They called it decentralized private computation, DPC, and they had many others contributions regarding the efficient implementation of ZK snarks and recursive proof composition. So these are how they do this. And they have also introduced and come up with a new set of elliptic curves. So 4 elliptic curves to be precise. And so in the abstract still we have a sneak peek of the performances cost. So our ZEXE transaction is 968 bytes. So if we are talking about two input to output records, so we're gonna talk about this more in details later. And the generation time is less than 1 minute plus some time that goes with the offline computation, and the verification time is tens of milliseconds. So and why they want to do this is at the end of the paper they come up with some use cases where they can apply ZEXE. So, for example, private decentralized exchanges for user-defined fungible assets and private, regulation-friendly private stable coins. So the content of this session with respect to the paper, so will be the introduction, techniques and definitions of DPC and construction of DPC as in the paper. So yeah, so these papers study 2 limitations of distributed ledger. So we all know them, so privacy and scalability. So this is because the distributed ledger or blockchain is based on this transparency consensus. So everyone is re-executing the transaction to do direct verification, and then everything is transparent. So there is no privacy per se. So there have been a lot of work that addresses those limitations. So so a better way to understand ZEXE is to look to the related work that addresses those issues, and the most famous one is ZeroCash paper, ZeroCash protocol. So they address the privacy of the content, privacy of the sender and the recipient within the anonymity set. And how they do this is by leveraging on zero knowledge proofs. But the problem here, if we want to do it in Ethereum or in any distributed ledger, is that the function or the transition state function will be different this time, because for example, in Bitcoin, it is only the cash flow of a single currency, right? So there is no hiding of this function. But in Ethereum, if you have, like, for example, ERC20, ERC720, so we need also to hide these functions. So not only we need the data privacy, but we need also the function privacy. And the scalability is the problem of the re-execution for the verification. So if you look at some related works that handles these two, so we can talk also about, for example, challenge and exit games relying on economic incentives. For example, Plasma. So yeah, so it relies on some economic incentives. So I'm not sure how it goes now in Plasma, but at some point it was like there have been an exit game, and then in a Plasma chain, if you want to retrieve your money back into the mainnet, you start an exit game, and anyone can challenge you. So this involves some economic incentive. But in ZEXE, we want to focus only on cryptographic proofs.
I know that just one thing. I know that like
Yeah,
TrueBit
sure.
is definitely like, I don't know where Plasma's at either for that, but I know that originally, and I think still, TrueBit, which is also mentioned there, that's just based on economic incentives.
Yeah.
There's like a game, like you said. Cool.
So other solutions that relies on cryptography is, for example, multi-party computation. So multi-party computation is you have a set of participants, and then each one has a private input, and they execute a public function. But this function is public still, so it doesn't hide this function. So you can keep private your secrets, so your secret inputs, but the function will be public. So there is a paper how, and then you have also, for example, this recent paper by Benedict Bunes, ZETHE, so which is basically doing confidential transaction into Ethereum. So confidential transaction, they were introduced in Bitcoin, in UTXO based blockchains. They were applied to Mimblewimble in Green or Beam, and to Monero. So, but in distributed ledger, if you have balances, the problem is, in confidential transaction, what you do basically is a pedestrian commitment, where you have a value and then a blinding factor, and then you leverages on the homomorphically addition of those pedestrian commitments in order to verify the equation, and then you need some range proofs in order to avoid the negative numbers. But the idea is, what if someone doesn't give you the blinding key? So it will block your UTXO. But in a Ethereum or distributed ledger, it will block the entire balance. So ZETHE is a paper to do this. And also you have hardware enclaves such as Intel HGX, but this is another problem. About ZEXE, so the contribution goes this way. So they have introduced a new cryptographic primitives called DPC, decentralized private computation. So they in the first part of the paper, they establish a formal language of ZEXE, so records, nanokernel, birth, death, predicates, and second, they have an implementation strategy, so they come up with a lot of contributions with this regard. So ZK snarks, recursive composition of proof, and another thing is the delegated DPC. So when you want to generate a proof, you can delegate this proof to some untrusted worker. And the size of the transaction, so if you have M input and N input, it will be 32 times M plus 32 times M plus a constant that is 840. So I said 968 if we have a two input to output transaction. So as I believe, the starting point of ZEXE was to extend ZeroCash, right? So in ZeroCash, how the privacy is handled and addressed. So you have coins, so fungible tokens, if you want to talk more generally about distributed ledger. So in order to create a coin, you publish a commitment to this coin. And in order to consume this coin, you publish a serial number of a coin. So a transaction will be a serial number of old coins, plus the commitment to new coins, plus some zero knowledge proof that attests that the serial number belongs to some old coins and commitment preserves the same total value. So you do this with Merkle proof, as in ZCash, for example. The idea is that you will have three parts: serial numbers of old coins, commitment to new coins, and some zero knowledge proof that attests of the correctness of this transition. So in ZEXE, they start from ZeroCash and they want to extend it. So a coin will be this time a record. So this is just to establish a common language in ZEXE. So a coin is a record. So if a coin is a integer value, a record is some data payload. So in transaction in ZeroCash is serial number of old coins. This time it will be serial number of old record, commitment to new record, and zero knowledge proof. So that's an arbitrary function was applied to all the records in order to produce new record. So in ZeroCash, it was only one single function, which is the cash flow. So this time we can, so we want any function to be applied to new record in order to all the records in order to produce new record. But then the problem is if you want it to be any function, so we want user-defined functions. So this will be a problem because we want the function to be private first, and we want it to be permissionless, which means that any user can choose any old coins and apply to them a new arbitrary function in order to produce new record. So this will result in a problem of isolation, because we will have some, for example, some users that are dishonest, that are malicious, and they will use some user-defined malicious functions. So how can you isolate malicious functions from honest functions? So in the paper they have proposed some solutions, and they come up with their solution at the end. So one of the solution will be to add to the set of zero knowledge proof, to add a new zero knowledge proof that attests that the same function was used. But this is quite limiting, because in other words, this boils down to the fact that you will apply ZeroCash to every token. So, for example, in Ethereum you have ERC 720, you have ERC 20, and then you will apply Zcash to everyone. Because if you isolate functions in a way that you add some zero knowledge proof that the same function is used. So for example, you cannot do some cross token swap in a zero knowledge fashion. So this was the first attempt, and the second attempt is to do some universal function on the ledger. So on the ledger you will have a universal function, and then your user-defined function will be inside the data payload. So one universal function and data payload as user-defined functions. So, but in order to execute different processes on the same ledger, on the same execution environment, we need to share some. Once again, so ZEXE language a record nanokernel. So which is a minimalist shared execution environment that allows to execute different processes without violating the privacy of each. So if we recapitulate, a record will be the data payload plus those what we call birth predicate to create a record, and death predicate to consume a record, and then we need some public input to apply those death or birth predicates. So they call this transaction memorandum, and then private information will be aux input. So for example, if we take this per example, we want to do some cross asset swap in Ethereum in a private and zero knowledge fashion. So we will create, so Alice, for example, wants 10 token A to exchange against 50 tokens B. So what she does is she creates this death predicate, and in this transaction memorandum, she says that if some requirements are fulfilled. For example, if someone knows the secret that opens a commitment, a hash functions, well, the atomic swap can occur. So those are for the time being just formal language introduced by ZEXE. So if we recapitulate, we have a record. So those are the equivalents of coins, but they are payload, the data payload, but not values. We have birth and death predicates. So those are user-defined functions. So per function, per record, and we need some public input in order to apply those predicates. So we call this transaction memorandum, and then everything that is private still is called auxiliary inputs. And also in the in this section techniques, they are talking about delegated DPC, delegated distributed private computation. I think we will talk about this more in details in next sessions. But the idea is we are doing proofs that assess to the correctness of offline computations. So an offline computation, a proof, the bottleneck of a proof in terms of time is the generation of the proof. So in their paper, they propose a way to give to an untrusted worker the ability and the right to generate this proof on their behalf without having the secrets, without revealing those secrets. So they leverages on randomizable signatures. If you read the paper entirely, they took Schnorr signatures and they extended it to some randomizable signatures. But we will talk about this maybe in next session. So if we continue through the paper, so yeah, as I said, many contributions were related to the technical implementation. So there have been some challenges, and they came up with some solutions. So those predicates, those birth and death predicates, they are user defined. So they are arbitrary functions. So if you want to create a zero knowledge proof on a arbitrary function, so you need some sort of whether you need a universal ZK snarks. So for example, there has been this paper Sonic, but it is not quite production ready for the time being, or you will end up with a ZK snark per predicate. So because if you want to prove a predicate, you want a circuit for this predicate. So this means a ZK snark per predicate. So we agree that universality is costly. So a solution is to do a proof of proof. So instead of doing a general proof for every single predicate, so a predicate is user defined. So we will end up with a proof per predicate. What they do is they generate a proof offline of those predicates, and then on the ledger they verify the proof. So this means a proof of a proof. But so on the ledger we will have a universal circuit that is a verification circuit of a proof. So a proof, for example, in ZEXE they took the state-of-the-art ZK snark. They took GM17. So yeah, the state-of-the-art with the simulation extractability feature. So they took GM17. In GM17, the verification is two equations and 5 pairings. So it is constant size. You have 5 pairing computation, but if you want to do it in Ethereum, you will end up with 6 pairings, because if you want to use the precompile in Ethereum, so you need all the elements to be in the J1 or J2 element. So you will have a pairing in addition, but this is not a problem. So the idea, it is constant. So we can create a circuit that verifies a proof. And then those predicates, so NP predicate, NP statements, we will create offline the proofs of them. But if we look at the literature for recursive snark, because this is what we want to do, even if it is only one depth recursive snark, because they do not need to do a proof of a proof of a proof of a proof. They just merely need a proof of a proof. So if we look to the literature, so especially the BCTV 17 paper, so they leverages on what they call the elliptic curve cycles. So because the problem is, so for example, let's take the example of GM17. So the proof in any pairing-based ZK snark, the proof is a set of points on the elliptic curve. So in GM17, it is 3 elements. So I've put an appendix at the end where I'm talking more in details about this. But anyway, so the idea is, yeah, so you have a proof is a set of points on the elliptic curve. So in GM17, for example, it is 2 elements in the first group and 1 element in the second group. So those points belong to a subgroup of order, say, n. And the verification is pairing computation. So bilinear maps, they take element in subgroups of order n, and they output element in an extension field p to the power k. So if you want to create a circuit that does the verification, so in the verification, so it is an extension of p, so it is a p arithmetic, but the generation of the proof, so you want to generate proofs of point of order n, so the generation is arithmetic of order n. So it will be nice if we can have this n equal to p. But unfortunately we cannot, because so the explanation, I've done it. So the idea is in pairing based elliptic curves, in pairing friendly elliptic curves. So we want the subgroup order to divide the field size power k minus 1. So if the field size is equal to the power if the field size is equal to the subgroup order, so the subgroup order will divide 1, so the subgroup order will be equal to 1. But we want the subgroup order to be a large prime. So yeah, we cannot find elliptic curves that has if p equal to r and still pairing friendly, because we can do if they're not pairing friendly, but then we will end up with an elliptic curve that has a Frobenius trace equal to 1, and then we know some attacks like smart attack that hack the discrete logarithm in those anomalous curves. Anyway, so yeah, so going back to their contributions, so empirically we know from this paper BCTV that we can create some pairing friendly cycles. So the solution to this mismatch in arithmetic is to do the first proof on a curve and the second proof on another curve, but then the field size of one will be equal to the order of the other, and vice versa. So there will be no mismatch. Or another solution will be to model the arithmetic in P by the arithmetic in N, but this is costly because we will have a log P, a log field size overhead. So the best solution, empirically speaking, is to do it with elliptic curve cycles. So this paper proposed a family of elliptic curves, so MNT family. So it was the first family ever to propose pairing friendly elliptic curves. So, but the problem is that they have an embedding degree equal to 4 or 6. So this is a problem because this is the parameters of the curve. So P is 149 bits. So if we reason about the security of the curve, so we will reason about the embedding degree 4, since it is the smallest one. So if we are 149, so the discrete logarithm in the target field, so won't be that hard, won't be 128. So they are not that good and that efficient at 128-bit security. So in ZEXE they come up with a new set of elliptic curves, not that perform well in 128-bit security, but they do just merely a proof of a proof. They do not need a cycle, because in a cycle you need the order to be equal to the size, but also the size to be equal to the order the other way around. So you will end up with a cycle, and then you will roll your two curves as much as you want to create a proof of a proof of proof of a proof. But in ZEXE, we want only a proof of a proof. So we can be limited to finding an elliptic curve that has an order equal to the size field of the previous one, and that's it. And we do not need the field size of it to be equal to the order of the other. Just a one-way function. So it is a as they call it, a bespoke recursive or a recursion, or a recursion of depth only one. So so one solution is to take, for example, an elliptic curve that is quite efficient at 128 bit. So we know few of them. For example, the elliptic curve we have on Ethereum, so alt bn 128. So this is an elliptic curve that is pairing friendly and that has 128 bit security. So, and if we look at the literature of pairing-based elliptic curves, we know a method to construct elliptic curves that has precisely an order, a subgroup of order R. So we fix the subgroup order. So this construction is called so this construction is called Cox-Pinch. So at the end in Appendix B, I guess I gave this so how we can do this Cox-Pinch method. So we know all these equations. So this has theorem, which means that the number of points on an elliptic curve is equal as is equal at the field size plus 1 minus some Frobenius trace. That is between -2 square p and 2 square p. An intuitive way to understand this is to look at Schwarz-Weierstrass elliptic curves. So we have y square is equal to x cubed plus ax plus b. So imagine if you have, so x is an integer between 0 and p minus 1. It belongs on f sub p. So if x goes from 0 to p minus 1, and then you have to resolve the equation in y square. So imagine you have one solution of this quadratic equation per x. So you will have p pairs x y, and then you will add to this the neutral element, because it is not a rational point, it is in projective geometry. So you will have p plus 1 point. But this is just an imagination where you have one y one y per x. But if the quadratic equation has 0 solutions, or maybe 2 solutions, so you will have p plus 1 plus or minus some those equations. So this is what we call the Frobenius trace, and there are many other ways to define it. But anyway, it is between -2 square p and 2 square p. So if we raise to the power 2, we have 4p minus t square is positive. So we will end up with this equation where d is a non-residue. So because this one is positive. So in Cox-Pinch, you fix the prime R, and you end up with an elliptic curve. But if we look to this equation, so we have t, we have y, we have t square, we have y square, and here we have t and y that are modulo R. So there is no q. There is no way to think that q wouldn't be equal to r square in terms of bits. So this is a problem, because if we take, for example, Bn elliptic curve, or so if we would take any elliptic curve that has a security level 128, so we want so the prime field size will be 256, because we want it to be secure to Ropolar algorithm, or to baby step giant step, that is in that has a complexity quadratic in P. So so yeah, so we will end up with an elliptic curve that has a lot of bits. But since in Cox-Pinch method we can construct pairing friendly elliptic curve with an arbitrary embedding degree. So we choose the embedding degree. So if we choose the embedded degree, we said that that Q will be equal to subgroup order will be equal roughly to the prime field size square, or vice versa. The prime field square will be equal roughly to suborder square. So we will have twice much bits. So then we can choose the embedded degree to be half the embedded degree of, for example, BN curve. So BN curve have an embedded degree equal to 12. So in Cox-Pinch, we only choose an embedded degree equal to 6, because the prime field is twice bigger. So this is what they did in ZEXE. So they constructed a Cox-Pinch elliptic curve over a BLS, but not a BN nor a BLS 1238. So if we go back to look at so elliptic curves that are used in distributed ledger for the time being. So in Ethereum we have BN128, and in ZCash, after the sapling activation, we have BLS 12381. So those two elliptic curves, they have the same embedding degree equal to 12. But the problem is efficiency if you want to do a proof of a proof, because the Cox-Pinch elliptic curve, so we will call it the embedded elliptic curve. So this embedded elliptic curve will have, it is constructed in a way that it has a subgroup order equal to the prime field size of the previous one. So we can construct this. I've played a little bit with SageMath recently, and I've constructed a Cox-Pinch elliptic curve over BN128, so the Ethereum elliptic curve. But it is not quite efficient, because the prime field size of BN is not highly two-adic. Or in other words, the prime field size -1 is not divisible by a large power of 2. And this is a problem if you want to do some A50 algorithm, some fast Fourier algorithms. You want the field to be highly two-adic. So you want it to be divisible by a large power of 2. So in BN curves, or in BLS 12381 that is used in ZCash, so both are quite good at pairings, because they have an embedding degree equal to 12, but they have a field size that not highly two-adic. So this constructed elliptic curve will have a subgroup order that is not highly two-adic, and then as the guys from ZEXE say, so it is better to find another elliptic curve to substitute BN or ZCash BLS, rather than using them with an elliptic curve that is not that much highly two-adic. So what they did is, they proposed a new set of elliptic curves. So the first elliptic curve is the one to substitute BN128 or BLS ZCash. So this is a BLS curve. So it has an embedding degree equal to 12. So I think that Hey,
Yusuf, I had a question when I was going through this. So as you said, you know, the authors chose that instead of doing recursive proof composition, they wanted to do this proof of a proof. And by using Cox-Pinch, this was somehow bounding recursion. It wasn't immediately obvious to me, I guess, how that was being used, mostly because Cox-Pinch method was new to me. Did you have an understanding of how that method was bounding the recursion, or kind of how that proof of proof instead was,
yes,
was
okay.
that?
So yeah, very good question, because the bounded recursion is not related to Cox-Pinch, but it is related to what they want to do. An unbounded recursive, or a simple recursion, is when you have two elliptic curves. So let's say E sub 1 and E sub 2. They have subgroup orders R sub 1, R sub 2, and they have prime field size P sub 1 and P sub 2. So a simple recursion is when you have R sub 1 equal to P sub 2 and R sub 2 are equal to P sub 1. So the relation is going the other way around. But
Right.
in a bounded recursion, you need only one elliptic curve that has another equal to the prime field size of the previous one. And as much as I know, I'm not very sure, but in pairing-based families, so if you look at, I think I should put the references later. If you look at the taxonomy paper by Freeman, so this paper is a very good paper when he gives all those families of pairing-friendly elliptic curves. To my knowledge, the only elliptic curve, the only family where you can precise the subgroup order is Cox-Pinch. So this is why they chose Cox-Pinch, I guess. Not sure, but I guess.
Is there any, I just wanted to also say if there's any other questions or anything else that people want to say, they should probably jump in. Where are you at right now? I'm trying to follow you in your notes. I just shared the notes, by the way, in the group so that if anyone wanted to look around. I realized that after the fact that you were sometimes referencing things a little bit further down.
Yes, I'm at the third point. If we look at the section definitions, techniques, and constructions,
yeah,
I'm at the third point, starting from the end.
From the bottom. Cool, cool.
Yeah.
Okay.
So I'm not sure if Matthew, this answers your question.
Well, I was just the question was actually to the group if there's any questions, if there's anything else that's been sort of you've been thinking about.
Yeah. So for this Cox-Pinch, I guess I need to look a little closer. For now, I could also understand that my knowledge of pairing, or how why their bespoke recursion is different than the other one. For me, this is all rather new. Just that seemed like an important point that jumped out at me. That just so coming more from the engineering side, I'm thinking, okay, the thing that's bounding recursion ought to be quite useful. So Cox-Pinch method will be something I read up on then.
Okay, sounds good. So
Youssef,
yeah, sure.
One quick little question. I should, well, okay. So, okay, this is a distraction. Apologies. So maybe it should be an email. But the one thing I never quite understood. So when they make these cycles of elliptic curves, there's the effort has always been to try and make a cycle where both curves are pairing friendly.
Yes.
And I've never seen, I've had some offhand comments that, oh, that wouldn't work or something, but I've never actually seen anybody try and do one where only one of the curves had a pairing and you just do another, like a bulletproof on the other curve. So you attempt to verify a pairing equations in a bulletproof, which I know would suck, but then you completely hide that. You never heard discuss this with anybody, or no, you can't say that why this doesn't work. Maybe that's a distraction. We can do this.
By the way, that's Jeff and Alistair. So if you noticed, Alistair's voice just changed. That's Jeff Burgess. Hi, Jeff. I didn't know you were there.
Showing an identity here, yeah.
Never mind. If this is too much of a distraction, continue. We can just continue on. Sorry.
I did have a question a little bit about the relationship between this and Sonics, because that one depth embedded version that you just described sound a lot like the way they describe Sonics. Is there a connection there? Do you know?
Well, the connection is so this entire point of doing a proof of a proof, because universality is costly. So instead of creating a circuit per predicate, or you just create one universal circuit that is verifying a proof that you have generated offline. So this is how they turn around the universality. But if Sonic, if there is an actual implementation of Sonic that has been proved, well, yeah, so we do not need this proof of proof. You just do a universal circuit on the ledger, and then whatever function you want to prove, you use the same you use the same circuit because it is universal. But well, it is universal in to some depth, up to some depth. Because for example, if you generate a circuit that has, let's say, 1 million gates, you can prove whatever NP statement that has less than 1 million gates. If you go beyond 1 million gates, you need another circuit. And then they have another nice feature that is updatability. So in ZEXE as well, they are talking about multi-party computation to generate the trusted setup. In Sonic, if you do not believe in this trusted setup, you just take it and update it. So it is updatable. But yeah, we do not need proof of proof if we can work with Sonics.
All right, keep going then.
Okay. So we constructed our first elliptic curve BLS that is highly two-adic with respect to both the group order and the field size. So the BLS in ZeroCash, for example, it is highly two-adic with respect only to the group order because, well, they do not care about the prime field size when doing FFT. And so in ZEXE, they constructed a new BLS curve that is highly two-adic with respect to both the subgroup order R and the prime field size P. So this is the first elliptic curve. And then they constructed a new elliptic curve Cox-Pinch over this BLS. So this is the second elliptic curve. So it has but it has some limitations because, as we said, R square, so the subgroup order square, is roughly equal to the prime field size. So it will be tedious to do computations over it because it is twice bigger. So here they did so to minimize. So they want to minimize operations over Cox-Pinch elliptic curve. So we have two elliptic curves. We want to minimize the operations over the elliptic curve that is heavier. So if it addresses privacy, so if it is a proof of a proof, so if it is related to those birth and death predicates, so to those user-defined functions we want to keep private, so we do the computations over Cox-Pinch. So it is a proof of a proof and it is private. And all other checks, the normal checks that do not involve privacy of the user-defined functions. So we do it over the BLS curve that has less bits. So it's not that heavy as the Cox-Pinch. So this is another optimization, and then another optimization, just like ZeroCash did after sapling activation. So they want to optimize the NP statement. So we have been talking about those zero knowledge proof for to prove that a serial number belongs to some old coin, and the opening to some commitment of new coins, and the same for records. But so those commitments are hash functions. And hash functions, so if you want a circuit of hash that does hashing, so you will end up with a huge circuit. So you want to optimize those circuits. You want to optimize those NP statements you want to prove. So Dyer Hopwood in ZeroCash, they came up with those Pedersen hashes. Yeah. So Pedersen hashes, so over Edwards elliptic curve. So here again, we need another elliptic curve. So an Edwards elliptic curve. So for example, in ZeroCash, they've called it Jub, and then they've done the same in Ethereum over the BN curve. They called it Baby Jub. So this is a curve that has a number of points equal to the prime field size. So the same as our bounded recursion, but it's not pairing friendly. And they define the Pedersen hashes over it. So in ZEXE, they did the same. So they come up with, so they have this BLS curve, they have this Cox-Pinch curve, and they have created their Jub-like curves over both Cox-Pinch and BLS. So we end up with 4 elliptic curves. So here in this table, so you have all those elliptic curves, you have the size bits, and so you have the embedded degree 12, 6. You have the two adicity. So the R-1 is divisible by a huge power of 2, so 47. So this is quite good. 46 is quite good. I think that in their constructions, they chose only those that have this is what we call the 2-adicity or the 2-adicity order. So that is greater than 40. I think there is a way to do this in BLS curve because, well, in pairing-friendly elliptic curves, you need a lot of requirements, and the best way to come up with a family of elliptic curve is to change those requirements from integers into polynomials. And if you do this with polynomials, so we will end up with a family, because at the end of the day, you will evaluate those polynomials into all those integers until finding one that clicks. For example, one that has those requirements you want, or prime integers, etc. So one way to do this is to substitute the equation of your polynomials with x to the power 40. I'm not very sure, but this is how you can do this. So in the notes, so yeah, so I have in this appendix just the steps in Cox-Pinch method. So I wanted to emphasize in this to explain that you will have a twice match bit. But then another thing is the complex multiplication method, because in Cox-Pinch method or in any other pairing friendly construction, so you will, at the end of the day, at the end of your method, you will just prove that there is an elliptic curve that has a subgroup of order R, that has a prime field size P, that has a Frobenius trace T, that has a discriminant, a complex multiplication discriminant D, and, well, all those integers. But then, what is the actual elliptic curve? So how can you write it? What are the coefficients of this elliptic curve? What is, if we're talking about a short Weierstrass elliptic curve, what are the A, what is the E, and what is the B? So yeah, we need what we call the complex multiplication method. So this is the from the complex multiplication theory. So we need to find a polynomial. So we call a Hilbert polynomial, a class of a Hilbert polynomial. Sub D, where D is the discriminant. We find the root, and then, well, the elliptic curve, the parameters turn out to be 3k c square. Well, I think that we should maybe sometimes do a session about pairing friendly elliptic curve construction. But, well, anyway, in Cox-Pinch method or in any pairing based elliptic curve construction, we need this complex multiplication method in order to come up with this A and B. So if we go back to the contributions of ZEXE, so yeah, so
this curve, I just want to ask this. So this curve means that we don't need many operations over CP to verify the things we're putting on chain. But how hard is it for the prover?
How hard is it for
offline?
Well, for the prover, it is always the same. And the bottleneck in the proof generation, if we're talking about pairing-based snarks, would be the multi-exponentiation. And yes, if you do it on CP, it will be
so we're doing the universal bit, the hard bit on CP, on the bigger thing. So I mean, if we had a recursive snark, we basically do everything on the easy thing, on the easy curve, right?
Well, if it is not related to privacy, we do it on the easy curve. If it is related to the predicate we want to keep private, we do it on the now easy
we're
curve.
doing everything on the difficult curve. Okay.
Yeah, because we are going to do a proof of a proof, so it is private. So yes, and the last point is, yeah, so in ZEXE they are using GM17. So the state of the art of pairing-based snarks is Groth 16, but it has this malleability that can be addressed in different ways. For example, in snarks using nullifiers. But, well, even in Pinocchio, we knew about this malleability, vulnerability, if we can say this way. So they chose to do it with GM17. So GM17 has this simulation extractability features, which means that it's not malleable. So, but it comes with a cost. So the proof size is always the same, 3 points on the elliptic curve, 2 on the first group, 1 on the second group. So and the verification in Gauss 16 is one equation with 3 pairings, or 4 pairings if you want to use the Ethereum precompile. And in GM17 it will be 5 pairings, or in Ethereum it will be 6 pairings. So it comes with a cost of verification, but I think we cannot do better than GM17 if you want the simulation extractability. For example, in Gauss 16, in the paper, well, Gauss said that, well, he proved that you cannot come up with a snark that has only one element proof, otherwise it will be linear, and so it won't work. And he came up with 3 elements, and as an open question he asked if we can come up with 2 elements. But in GM17 they proved that you cannot come up with like 2 elements. So this is like the state of the art in terms of size of the proof if you want the simulation extractability. So whether in GM17 or Gauss 16, or pairing-based ZK snarks, or what we call the pre-processing ZK snark if you want to be more general, we need a trusted setup. So yeah, a trusted setup. So we need this transcript. So in GM17, so yeah, they are doing the same as ZCash. So a multi-party computation where everyone adds to this secret. So for example, the powers of Tor. And well, as long as one of those participants gets rid of his secret, so yeah, so it works. But I think Sonic would be a nice thing to think about if you want to do offline computation.
Yeah, this is something that I'm always stuck on, is like, when do you do that, and how often do you actually have to do it? Like in the build that this is proposing without Sonics.
Without Sonics. So yeah, so you need a trusted setup per circuit. So for example, in Zcash, they have always the same circuit, which verifies those ZKPs that are the serial numbers belongs to these old coins. So you need a Merkle proof, path authentication. You need opening to commitment of new coins, and then you need also to verify that the total value holds. So if you are doing 2 input coins, 2 output coins, or 2 input record, 2 output record, you need to verify that A plus B is equal to C plus D. So this is one circuit. I'm not sure how many gates it has, but it is always the same circuit, and it is always the same function, that is the cash flow of the single currency. But in general, in zero knowledge in ZK Snark, if you need to verify a new thing, you need to create a new trusted setup. But in Sonic, we'll just create one trusted setup, and then as long as your function has less gates than the trusted setup, you will always use this same circuit.
Cool.
So yeah, and then in the note I've added those appendix where I explain maybe a little bit more in details. So the recursive stuff, and that's it. So yeah, the technical terms. So as Matthew mentioned, so we are not doing cycles. This bounded recursion, we are doing chains. So cycles, they overlap. So you have, for example, a 2 cycle, you have 2 elliptic curves. So you have relations in both ways. So if, for example, if you have a 3 cycle, you will have 3 elliptic curves. So 1, 2, 3. So you have a relation between 1, 2, between 2, 3, and then between 3 and 1. But the technical term, if you want to say, is chains. So we have a relation between 1, 2, and between 2, 3, and that's it. We do not overlap. So here we are all only reasoning about 2 cycles or 2 chains. So 2 elliptic curves. So a cycle is a relation between 1, 2, and 2, 1. And a chain is only a relation between 1 and 2. So one way. So it is a bounded recursion. And yes, I think that's it. On my side, there is a GitHub called EC Factory for Matthew. You said you come from engineering, so there is a SageMath repo where you can play with those elliptic curves. You can construct Cox pinch. You can construct MNT curves. And then you can play with them if you want to understand this more, or for those who want to understand this more in mathematically speaking. So yeah, so there's a lot of literature. I guess I haven't added the references yet, but I should add all those papers I mentioned.
That's so cool. Yeah, the fact that do we actually need one trusted setup per application? Per birth and death predicate?
Yes, we need a trusted setup per predicate, but this will be like offline. But what we do on the chain, so I think this is some term in the paper, they call it a master circuit or a master trusted setup. So if you remember, we said that if it is related to the user-defined function, so if it is related to the privacy, we do the computation over Cox pinch. So it will be a proof of a proof. So a proof of a proof is a circuit that does the verification. So it is the same circuit. So we need only one trusted setup to do a proof of a proof, because it will be always the same verification. The verification of GM17, whatever the predicate is always these equations. But then those are the checks that are not related to functions. Yes, you need a trusted setup, but those do not.
You can do trusted setups later for when you want to use something.
Yes.
But it means that our set of applications can't be too big unless we want to do a lot of trusted setups.
Well, it's up to the users. So if the idea is we have a universal trusted setup to do proof of proof. So for those birth and death predicate, and then other checks, it depends on the application we are talking about. So maybe there is no other checks rather than the predicate. So it depends on the. So this is from a theoretically point speaking based on the ZEXE paper, but we have to look at the DEXE, for example, application, or maybe the atomic swap, or maybe the stable coin privacy. So maybe we will see more in details if we need those additional checks or not.
That was a lot that you just got through in an hour. So congratulations. That was a feat, I would say.
But I think because the first part of the paper was pretty much everything, right? But well, maybe not in details, but
sort of, yeah. It's sort of the overview. I'm wondering, is there any other questions or anything? Because like I know that one of the co-authors is in the group, and he was asking if we have any feedback or any thoughts.
Yes.
That we can share.
I had a question, if that's fine.
Sure.
Youssef, you said the verification is always the same, which is then you said that you basically have a single circuit to the proof or the verification of the proof or whatever it is. I'm just wondering, when you have public data,
yes.
when you're verifying a snark that includes public data, then you have to include this public data in the verification. You basically complete the proof using the public data. Does that mean that the proofs will be, as it were, complete? There will be no input by the verifier, as I insert the public data at this point or something?
Okay, I've got your point. So yeah, so for example, if we take GM17, for example, verification. Yeah, so this is the equation of the verification. So so pi sub A, pi sub B, and pi sub B sub C are the proofs, and VK delta, VK gamma, and VK alpha beta are the verification keys that are pointed on the elliptic curve. And this X is the instance. So yeah, it depends on the public input, but what we want to do is a universal prediction per application. So if you want, for example, to do a DEX, it will be always the same verification. If you want to do a private atomic swap, it will be the same verification. So to my understanding, but I may be wrong. But yeah, the idea is, yeah, you're right. It is always, this verification key is related to the instance. So you need if your public input, so your instance changes, so you need to change this verification key vk sub x. Or do you
Okay,
agree? Or
yeah. Yeah, that's fine. I was just looking for the button. Thanks.
Oops, I forgot I was muted. Yeah, I was just talking to myself there. Do we have anything else we wanted to bring back to Pratouche? Any other sort of thoughts so far? I guess not.
It is only on my side. No, okay, it's fine.
Cool. Well, I think we're at time. I wondered, how did you guys feel about this? Did you get something out of it? Like, it's interesting because there's no way, I haven't seen anywhere where you can actually see such a detailed walkthrough of this paper, and this is helpful, definitely.
Yes, I think the only video that is available on YouTube is Prayuch video, and he only presents the
use cases.
The use
And like
cases.
very, very, very overarching.
Exactly.
Yeah, this is detail that's not really in the paper. You have to sort of chase up all the references to get this.
Yeah.
It's very interesting for you to us to see it.
Cool. So yeah, I think Yusuf, this was really great to do. I think it would be cool to do. I mean, our plan is to definitely do 3. Do you think 3 is too little? Do you think we should actually break it down further, or do you think we could do it in like another 2?
I think what we haven't covered yet is the delegated DPC. We haven't covered it yet, and we haven't covered also the use cases. So DEX, private atomic swap, stable coins, and yes, we also, if you want, we can go through more in details this bounded recursion and all those details. But those points we haven't covered them at all. So delegated DPC and the use cases.
And you also mentioned the elliptic curve, constructions, and just like that in itself could be a session. Maybe
Yes.
maybe not part of this, but it was just kind of a point of takeaway for me.
Yes, I think yes. This would be very interesting if we can have like a session about elliptic curve construction in general, or about pairing-based elliptic curve constructions.
I wonder, we might want to look around for something like that for like a class or courseware or something, because it would be cool to see that like in a broader way.
Yeah. I for one, I guess I'm interested in that, because at a distance I heard someone saying about the Coda Protocol project. Oh, they only spent so much CPU time finding their pairing, and I could only take that really at face value, because I don't quite know how to do elliptic curve pairing, or what are the pros and cons, or how do you even solve that if you're just exploring a space of paired curves. So maybe that even turns into a bigger theme for us, but doing a beginning of that would be really good.
Cool.
Yeah, that sounds good.
All right then. So I'm going to shut down the live stream, and I just want to say thanks to everybody, and thanks again, Yusuf, for putting this together. It was really cool. I'm excited to rewatch this video too, because there's some parts where it was pretty dense, and I'm going to have to double check him. But
yeah, thank you, Yusuf.
Thank you.
Thanks,
Yusuf.
Bye-bye.
Ciao.